Dr. Franzu Zia, who's the guest editor of this collection, and Franzu is leading that particular collection on atomic force microscopy. So briefly, to introduce Franzu is presently working as a postdoctoral researcher at MIT, Massachusetts Institute of Technology, USA. And his current research focuses on new application areas in the rising fields of 2D material studies for advanced material property characterization. And his ongoing work aims to extend advanced AFM imaging modalities to handle demanding samples in extreme environments where interesting phenomena can generally be observed. And moreover, AFM-based nanorobotic manipulation and nanofabrication techniques are also being actively investigated for in-situ sample processing and characterization. Franzu received his master's and PhD from the MIT Mechanical Engineering Department, and Franzu's doctoral work focused on the development of next-generation atomic force microscopes to enable new imaging modalities such as high-speed imaging and specialized environment imaging. And Franzu has several publications and numerous awards to his credit. So today, Franzu will provide us with an overview of the recent advancements in atomic force microscopy. And right after his presentation, we'll be having a short quiz break. And two winners will be announced right after the quiz, and they'll be receiving exciting prizes from Joe. So stay tuned to Franzu's presentation. And without further delay, let's welcome Dr. Franzu Zia, who will be chairing the session today. Over to you, Franzu.
All right, thank you very much for the introduction. Let me start to share my screen. Okay, hello everyone. Welcome to this webinar with topic on recent advances in atomic force microscopy, particularly for surface property studies. So I'm Fang Zhou from Mechatronics Research Lab at MIT. So I'm the special issue guest editor of this AFM specialized methods collection. And today I'll be giving a general introduction about this exciting field of the AFM. And then the general aspects I will be talking about will be first a quick overview about the operation principle of the instrument. And then since my PhD work was actually in creating the instrument itself, so more on the precision mechatronics as well as instrumentation aspect. So I'll be talking a little bit about that so that this new kind of development to enable different kind of capabilities can be introduced. And then we'll talk a bit about the application side, which is combining AFM with different types of modalities, just as shown in the image here. As you can see, there are magnetic fields, there are electrical signal happening between the probe tip as well as the sample, as well as optical things. So let's get started with a brief introduction about the AFM system itself. So AFM system, as an overview, we particularly start AFM with the surface characterization, including topography, as it's a very basic modality. For imaging at this nanoscale resolution, we sort of need the three key subcomponents in the AFM system. First one will be the cantilever probe, which for a passive one, which we'll talk about what is passive, what is active later in the next slide. So this probe here, we can see it's a very typical one people use in research. We have the space support chip where we keep the tweezers on, and then we have the actual cantilever with a sharp tip at the end of it. This is the key or the centerpiece of the AFM so that people utilize it to interact with the sample. So for the interaction, usually on the nanoscale, we need a positioner, which includes some engagement mechanism. That's the coarse motion to bring sample and tip into contact, as well as the fine piezo tube, or usually some piezo-based scanner for motion control. Speaking of motion control, obviously we need some advanced stabilization system to implement the controller so that we can regulate this motion of the piezo scanner and then generate the desired image. For the probe, we start talking about the passive ones, which we usually does not have any MEM space components on top of it embedded, so that its deflection usually is measured by the optical beam deflection sensor. For experienced user of the system, you'll be quite familiar with this process. So you first need to align the laser to the cantilever and then adjust the quarter photo diode so that you can get the signal at the center of it. So later you can use it for this measurement of the deflection. Other than sensing, for certain operation, especially in dynamic modes where you need to excite the readiness of the cantilever, piezoacoustic actuation is typically used. So you have a piezo actuator at the base or the holder of the probe, and then you acoustically excite the vibration by driving a sinusoidal wave to the piezo actuator at the readiness frequency of the cantilever, which sometimes needs to be identified during the experiment before you start the imaging. So this is a very preliminary introduction. And then since we talk about passive probes, we can look a bit into the active probes, which is a rising field that people have been developing. Different principles have been utilized in the aspect to enable new capabilities, as well as letting people drive this cantilever using different kind of mechanisms. So now let's take a look at this very cool AFM precision instrumentation techniques. So I actually have a paper publishing summarizing the different sensing and actuation principles. The dominant ones, not only in the commercial system, but also in research, have the 6 different sensing principles, starting from this basic quarter full diode-based optical beam deflection system. People have been using this so-called stigmatic detection system, which is a typical principle used in getting DVD or CD drive signal. And then it can be similarly applied to the AFM cantilever to measure its deflection. Other than that, we have this optical-based interferometry detection, where this is usually used in fiber-based system for AFM operation in a very low temperature environment, where this optical access is very hard to get. So fiber can guide laser better and get more flexible path into the very small area of the chamber in some cryogenic environments. And then there is also some optical coupling using fiber-based technique, basically in similar way for this guiding into the system. Other than that, we also have a piezoelectric sensor as well as piezo-resistive sensor. Both are embedded, considered as because their elements can be put into the cantilever itself through nanofabrication. This allows the development of what is so-called active probes, basically because they don't really require external components. You only need to get this wiring to the electronics on top of it, and then you can get the signal out. So this is for sensing. For actuation, we also have many different methods other than the piezoelectric acoustic actuation. So first we have resistive heating, which you have the serpentine-shaped aluminum wire embedded onto like a 2-layer AFM cantilever, and then you can sort of like use this heating to get the temperature gradient in different materials with 2 levels of thermal coefficient expansion, and then you can deflect the cantilever. Similarly, you can use the optical source to heat it up rather than using electrical. Basically, it's just the optothermal heating. And then we can also use electromagnetic force, basically with a magnet plus a current flowing through it. And also we'll have this so-called electrostatic actuation, where in conventional large-scale system, electrostatic force is too weak to do much actuation. But on the small microscopic scale, this can be used to drive the AFM cantilever. Whether in AC and DC mode, this is a very, very interesting thing. Similarly, for the heating aspect, they can also drive the cantilever not only in AC readiness, but also deflect it. This can be important for certain applications, which we'll talk about a bit later in the next section. In the end, the piezoelectric effect, or the converse piezoelectric rather, can actually be used to drive the probe as well. So not only do sensing, but also do this actuation. As a summary table, there is like a 12 total principles where we can group them by whether they can do sensing or actuation or do both, and then talk about whether the signal is DC or AC only. Usually for piezoelectric, it's usually AC only due to the charge leakage problem. For other methods, basically they sort of can do both DC and AC, but piezoacoustics is a bit tricky depending on where you put the actuator. It can be on C only for most of the time. For the size and location, bulk external means you need some big optical components or external components so that you can move the thing or get the sensing done. But for embedded, you can actually get this with a very compact form factor, which can be beneficial in certain applications. And there are, of course, certain limitations corresponding to each of them, basically. So what we have currently is about like the principle level understanding. Let me now show you a bit of the instrumentation examples that I've been using in my lab or my PhD work during the past several years. One example would be the active probe, which is the piezoresistive bimorph probe. As we talked about previously, we have this aluminum serpentine heating wire shape for 2 layers of different material, mainly silicon and silicon nitride. So we can heat this up and then bend this cantilever. Later, we can use the piezoresistive element to embed it onto the very base of the cantilever, measure this deflection signal. So this can be used for AFM imaging with comparable resolution to our optical beam deflection system, so that it's a very powerful tool, but without the need for external box system. This can enable a number of applications, which we'll talk about later. So for fabrication, as we can see, MEMS technology are obviously used not only to produce the cantilever and the tip itself, but also the active elements, including the p-dope shaped silicon for the piezoresistive sensor, as well as the aluminum heating wires. So here are some pictures about the probe. It's actually mounted onto this SD card shaped base, so that people can handle it easier, because you only need to plug this into your probe holder and then directly start the engagement and imaging. No laser alignment needed. As you can see, probably one significant benefit would be, you can do plug and play without much experimental overhead. Just move forward to it. One important technique that's enabled by this probe, as I have demonstrated previously in one of the publications during my PhD years, is to coat this probe with a layer of protective coating to get these active elements protected. And then it can handle chemically harsh environment. And also the benefit is, since there's no optics involved, you can do imaging of this kind of probes in opaque environment, meaning no laser path can go through there. Some example would be some raw blood sample, or as well as some a crude oil, which we have done some imaging for in those areas. So the application again will be shown in the next section a bit more. This is just a brief mention of it. Of course, there will be some shift in the resonance, but in general, the imaging capability is preserved, and then we can do some calibration gradient imaging to verify that. Okay, we talked a little bit about the probe now, and then let's move a little bit to the scanner, but this scanner is more on the precision instrumentation stage. I'll just use one slide to show you what we mean by that. So this is the AFM scanner design. I have went through multiple iterations for different purposes. As my previous work is on high-speed imaging as well. So this is a 2 generations of high-speed imaging scanner that we developed that can move up to 10 gigahertz, meaning we can scan 10,000 lines using a sine wave for 1 second. So we actually did some video from that. Nowadays, commercial AFM has also high-speed applications, especially for biological sample studies, which you can observe the dynamics. So other than that, there is different strategies for designing scanners. Not only for overview and zoom, we can do both high speed and medium range. This is to get the trade-off between range and bandwidth. So basically, these are the 2 generations of that we have developed without going into further details. And last one we have played around with is using a speaker of the buzzer as a scanner actuator, so that we can drive some scanner at a very low cost, basically compared to conventional piezo-based actuators. Amazingly, this can also do AFM imaging. I designed this basically for educational AFM that have a cost of $4K US. So this is currently one version in our lab that we use for education purpose. So this is about instrumentation, but for application-wise, it's more interesting to see what the potential promise that AFM have in terms of going beyond modalities. So I want to start with one paper that I'm about to complete and include into our special issue of this Masters collection. We have this active probe AFM, as we talked about before, and we are trying to make it for large area imaging, meaning we have, for example, the semiconductor inspection task. So the idea is you can not only use one cantilever, but to use multiple cantilever to image the sample at the same time. So it's instead of using one finger to feel it, you use 5 fingers together. One example is this 4 cantilever in parallel active probe array, which can be used simultaneously in parallel for imaging purpose, and then stitch the image together to cover a fairly large area. So the separation of each cantilever is 125 micron, combining 4 of them with a scan area also 125 micron. You can get essentially a 0.5 millimeter range being imaged. So this is a very powerful increase in terms of throughput. As we know, AFM imaging is usually like relatively slow for conventional system. And then moving on to high speed, we look more into dynamics of local area. But this one can help you to cover a large area with stacked samples, but at a reasonably high throughput. So this will later be also include this methods collection. If you're interested, you're more than welcome to come check it out in the future. So other applications for the high-speed thing we talked about before, this is like one of the images we took in the lab for like calcite action process. So basically, this is a dynamic video we capture at a single location, but it actually shows how these pits are formed at the action process, and then the video just illustrated this entire process. So instead of looking at the beginning and the end and guess what's happening in between, this one allows you to understand what actually goes on between these two events. So it will be a continuous video stream. Also, as promised before, there's this imaging in chemically harsh opaque liquid. This one is in crude oil. Basically, the color is very dark, and then if you go deeper, not much optical things can penetrate through, and then you can only do imaging with conventional setup. But with the active probe, we can do that. Okay. Now let's move a little bit more into an outlook about the imaging modalities and what we can enable with AFM. On the general high level, we want to classify AFM imaging modes into 3 categories. One is we call them contact modes, which we obviously make contact between the probe and the sample always. And then we have dynamic modes where the redness is excited. And then we have something called the jumping modes, where we have this probe and the sample make intermittent content, and the redness of the cantilever is not deliberately excited. This is typical if you're using Berkeley FM with their peak force tapping, although they have a tapping line, but there is usually doing this jumping mode. Under each category, there are many different sub-modes that have been enabled. I will not go into all of the details of each of them. You will see lots of examples in the method collection in the future, but these are the corresponding subcategories. And then we can not only do topography, but there is a combination of imaging techniques with various other, for example, spectroscopy, magnetic electrical signals that are all be included. So this will be very helpful techniques. Other than these basic categories, you have hybrid modes. For example, the contact redness will be a very interesting example where you make contacts always, but also the redness will be excited so that you can get those viscoelastic property of the material in the dynamic form. Other than imaging, you can also move on to nanofabrication, which these techniques based on AFM include lithography, deposition, manipulation. So it's a very versatile instrument which allows you to do this kind of things with in-situ imaging capability. Okay, just to show more images about examples, one is for 2D materials characterization. As you can see, this is first on the left-hand side, purely response force microscopy, which can reveal the sublattice, we'll call it superlattice, in this 2D material, where we have 2 layers of material and we stack them at different so-called twist angle. This is the field in 2D material rising as twistronics. Periodic response force microscopy is one technique to reveal those stacking orders and those superlattice, which is formed between different stacking layers. Not only for the force response, but also you can use the near field infrared imaging combined with the AFM with super high spatial resolution, breaking their diffraction limit to reveal there are certain domain wall boundaries within those stacking 2D materials, which proves this AFM technique combined with techniques of spectroscopy becomes a powerful thing to evaluate the samples and reveal previously inaccessible situations and this kind of sub-features beneath the sample, which originally is not captured in the topography. For biomedical, you can see people use nanomechanics indentation process to study those material property a lot. And also, people also use this infrared norm-based scanning near-field optical microscopy to reveal this special area where we have certain chemical composition change into the tissue. And in this case, it's a collagen fiber to see if something is not right in that area or there is some pathological condition. So this will become like another area of applications. Moving forward into this fabrication aspect, so we have this fluid FM, which people use a channel in the FM cantilever, and then you have a small opening. If you inject this pressurized liquid through it, and this thing can be electrochemically controlled for deposition, you can do some 3D structure printing on a very small scale. So this is like obviously a micro nanoscopic 3D printing, which helps you to create those geometries. This probe can not only be used for this printing, but also you can, for example, sample some things from a cell by penetrating through it and then suck some liquid out. So this is a very powerful technique for biological research if you want to use it as like a nano pipette. Okay, so obviously there are a lot more applications. Currently, there is 3 publications already online that you can check out in this methods collection. And there are many new topics for incoming papers. Actually, you can see some abstract already. So there will be this spectroscopy combined with AFM, also a high-speed AFM, parallel active core extraction, nanomechanical indentation, phase response, nanoscale infrared spectral. So there are a lot. So these are like the promise of this collection and the general area that we want to go into, just to see what new kind of applications we can use with this AFM, whether it is a conventional technique applied to the new samples or imaging situation, or whether it is a new imaging capability enabled by this instrumentation level improvement, so that we can see a big whole picture about what is going on. All right, moving forward, we know AFM is a powerful and versatile instrument for nanoscale surface characterization. And then it is also an active field of research with various new imaging modalities being developed. This concludes the technical section of my talk, and then we'll move forward first with a short quiz on AFM topics. And then we'll have Dr. Celine Kelly to talk about this her new paper in this collection. Just a brief bio about Dr. Celine. She obtained her PhD degree in enzymatic engineering from the University of Technology in Champaign in 2003. After that, she got familiarized with the AFM in her postdoc experience in Germany. And then later, she joined the Phantom Science and Technology Institute as a faculty member, starting in 2006. Her expertise will be in this biochips, bioengineering, microtechnologies, and nanostructured materials, with a specific survey in nanobiosciences. After her talk, we will have a final Q&A session. So with that, I think we can move forward with the quiz first. Thank you very much. Yeah, so there will be a total of 5 questions, and then we will have like 5 minutes for that. So take your time on each question. It should be really simple questions, but help to refresh the memory about each subcategory.